So the regressions that we're doing now is not really a total look at regressions. We're doing this to the extent that you did it last year, since that's what we're trying to make up for. And next year you'll do it more, and then next year you'll do it much more. So generally speaking, the reason that you want a regression function is because it models the data with an ordinary written out function. If you tried to legitimately write out the function of plotted points, you'd have to just list them. But if we use, and then it wouldn't even probably be a function because you probably have two matching x values with different y values. But if we can model it with a function, then we can make predictions. And I don't think you made predictions last year, and so I don't think that's the goal right now. Definitely that will be part of the goal in third year. So you want to be able to say this function looks approximately like blank. And the only ones you're looking at actually are linear, exponential, and quadratic. I've included the cubic parent function here, just as a point of reference. Because really a regression function could be anything. Certainly any polynomial could be created through matrices actually. But so for right now, we're looking at these three, this one, this one, this one. And this function also, if it wasn't x cubed, if it was x cubed plus something, x squared plus something, x plus something, this one would look really more like this. So that does appear in regressions. But anyway, this one could be like this, or it can be upside down. And the quadratic can also be upside down. The linear can be going down that way. It's just the general shape you want to look for, whether it's right side up or upside down. So generally speaking, you would have an exponential regression likelihood if you had something that generally followed that exponential graph, or if it generally followed going down this way. So it doesn't have to be exact. The closer it is to exact, the closer it is to either 1 or -1 for R. And R is the correlation coefficient, but the R is for regression. For it to be quadratic, we just need to kind of generally have the points plotting around something that looked generally quadratic. So if we're trying to decide if it has a quadratic regression or exponential or linear, which one of those is the best fit, we can look at it. If we're given a visual like this, we can look at it and say, that kind of looks blah. The next slide, these are all based on linear. If you were to take the most basic version of statistics that did not focus on technology, which is not what we're doing third year because we're doing the on-ramps, but if you were going to do that, then you would only look at linear regression and nothing else. So this is an example just based on linear. So this is fairly linear. If I drew a line through this, it would match pretty well, be a pretty good predictor. Obviously my line's too fat, but that's pretty linear. It's also got a negative slope. So it's negative, and it's very close to -1. Negative just means essentially that your leading coefficient would have been negative. So this one has a negative slope, and the slope is the leading coefficient on the line. If it were quadratic, then positive would mean like this. But R being negative like this means as one goes up, so as x goes up, the other one goes down. This one is still negative, and it's still kind of linear, but it's not as tight to the line as this one. So it's not as close to -1. This one, you don't know if you should draw the line up or down or what. That's just everywhere. So whether you're looking for a linear a linear regression or any other kind of regression, this one doesn't have it. There's no function in there. It's just a big mess of stuff in a giant circle. This one is up, so it's positive, but it's about the same tightness as this one. So it's still 0.5. This one is 0.9. It's about as tight as that one is, or I guess exactly as tight. There's a kind of complicated way that you calculate the correlation coefficient. Well, in my day it was. These days it's you tell the calculator to calculate it for you. But anyway, so that's the same strength of predictability, essentially. So if we were using this in the way that we're going to use it in third year, we would say, okay, so suppose you find a new guy who has this X value. What should his Y value be? And you'd predict it like, you know, there. And then the amount that you were off would be less than if you try to do the same thing over here. And we'll use regression to calculate the error exactly. So this one would have more error than this one. And we'll do that in a couple years. This one has a regression correlation coefficient of 1 because these are on a line. So if it's actually on the curve, exactly on the curve, it'll be 1 or negative 1. And if it's very close but not right on it, then it'll be, you know, 0.8, 0.85, 0.9, and so forth. And 0.5 is, it's a weak correlation, but it definitely is 1. You can see that these values are related. Generally speaking, if you go up on one, the other one goes up. So they are related, but not strongly. These are examples that are not linear. So this one's positive and linear, because even though it's kind of fat around, it still just swoops up. Generally, if it's what we would call a football shape, skinny football, fat football, if it's a football shape, it's linear. So this one's negative and also linear because it's a football shape. This one, again, giant mess and nothing. You can't predict anything. As one goes up, the other one does whatever it wants to do because they're not related. This one, honestly, is probably a cubic relationship because this seems to kind of go out like that, so it probably would, as far as predicting from here to here, a cubic would be the best thing. But at any rate, it's not linear. But it is related. You can imagine a curve that it follows. This one is again linear. Oops. That line goes through it, and basically the function that best models the data is the one that has the same number of dots above it as it has below it. So you're trying to split the data in half so that at each spot you can predict with an error that's the same as every other spot. This one is not linear, and this one, if you remember your parent functions, now this one looks exponential. It could be quadratic, but it's awfully flat there to be quadratic, so I'd say that it's probably going to be a better fit to something exponential. This one looks pretty quadratic, not exactly, but fairly, so you could probably get a fairly good fit with quadratic. But between the ones that we're using, exponential, linear, and quadratic only, this one fits linear, this one fits exponential, and this one fits quadratic. If you have to choose between the three, those are the ones that fit those best. So now I'm going to go to this regression calculator, and I'm actually not going to use the one that had to know that uses quadratics only, that does quadratics only, because while it gives a lot of information about how you calculate things, it doesn't actually ever give you R, as far as I can tell. So we're just going to stick with this regression calculator for now, and Ms. Hirsch had provided you with this one, quadratic one, and I think Metacalc, and maybe a way to do it through Microsoft Excel, and certainly you can do it on the TI Inspire. But you probably don't have a TI Inspire at home, so we're just going to, for this moment, use this one. So I'm going to make something up, and I'm going to make something up that's kind of generally exponential. So I'm just going to give values here, 1, 2, 3, 4, 5, and then I'll say 5, 27, 122, 633, and 3220. Okay, so I'm purposefully trying to make it fairly exponential. And then we just hit calculate. And it's going to give us 4. It's going to give us what it calls power, which is not necessarily quadratic, and then exponential, and then linear, and logarithmic. And this you're not going to look at right now because we're not looking at logarithmic regressions at this time. So what we want to do is now look at R. R here is 0.8085. Here it's 0.9999 because remember exponential is what I was aiming for. 0.9736. It turns out I got fairly close to a quartic, although I didn't mean to. If we had more data, that would not have happened. But this is the closest to 1. And if these had been negative, I would have been trying to choose the one closest to -1. So if I'm asked right now to create a regression for this, and incidentally, if it was closer to quadratic than anything else, and we're looking for the one it's closest to, this power one would have been closer to quadratic instead of this 4. So then you would have known this one was the best, and then you could have gone over to the quadratic and used that calculator. So right now though, this is the one I want to use. So if I were taking the quiz right now, remember we're supposed to round to the nearest hundredth. So I would go put 1.02 and stop there because I'm rounding, times, and if I round this, I get 4.99. The 7 makes this round to a 0 and this round to a 0, so I'd make it 1.025 to the x. And that would be what I answered in the quiz. And anytime you're asked for a regression equation, it's always going to be y equals, and then for the moment, either a line, something that looks like a number times x plus a number, or an exponential, a number times something to the x, or a quadratic, y equals something square, x squared, something times x squared. So when you're asked for a regression equation, your answer can't be a number. It has to be a function, either a linear function or an exponential or a quadratic. Okay, so to test out my theory on the quadratic thing, I'm going to make something that's essentially quadratic now. So again, I'm making up the numbers, but you'll enter the numbers given to you. So I'm going to make this 2 and this 5, 8, 15, and 26. And then calculate. So we have, actually this has the best match at exponential, so maybe I chose poorly, like making up my points here. Okay, well I've made them a little more quadratic so that they match this a little bit better. So this we would then say, okay, let's go get a quadratic because it matches more a power function. So then I would come over here and put these 1, 2, 3, 4, 5. I really prefer this in the TI calculator. It's essentially the same thing. You put in your lists and you tell it to calculate regression, and then it would go ahead and do the quadratic with R and everything. So really when you're doing this at school, this is going to be way better for the time being, because anytime you put in a function, that's going to be graded by hand. If you choose incorrectly on a situation where it's quadratic, that's going to be okay. I mean, I'll count it if you've gotten something that makes sense and is close. The ones where you're looking at it visually, hopefully you can tell the difference. Those, there will not quite be the leniency. But okay, so this is the quadratic regression that I suppose this would be acceptable for this set of data, and so would this. Again, in both cases, go ahead and round to the nearest hundredth for each one. Okay, so hopefully this is enough information for you to do what we're trying to do. And if not, send me a message and tell me what's messing you up, and I'll try to make another video.